Hey guys, it's Ryan. In this video we're going to look at volume of distribution. I think it's one of the more complicated concepts of this unit, so hopefully this video will help just a little bit. So the volume of distribution is best defined as the apparent volume into which a drug distributes into a body's water. And just like pKa and bioavailability, every drug has its own VD. For example, warfarin has a VD of about 8 liters, ethanol has a VD of about 45 liters, and these are all set reported values. So if we were talking about constants for a particular drug, they would include the pKa, bioavailability, and the VD. But volume of distribution, they're reported for a 75 kilogram average healthy patient. And we may need to slightly adjust the volume of distribution if the patient is different from this average. And we'll talk a little bit more about that later. So here is our VD equals Q over Cp equation, just for reference throughout the video. So it's volume of distribution, and then we have the dose that's absorbed by the patient and divided by the plasma concentration after distribution has occurred. So if we boil concentration down to its most basic form, it's mass divided by volume. So if we had a container with some volume, some amount of drug or any molecule inhabiting that volume, it would be the mass of the solute divided by the volume of the solvent would equal the concentration. And that would be for one container. So now we could rearrange this equation, multiply by volume to both sides, and divide by concentration, and we get volume equals mass divided by concentration. And you'll notice this looks very similar to the equation that we're using. Only we have Q for dose, but remember dose is usually given in milligrams, which is a mass, so that makes sense. But notice that the concentration in our equation is for the plasma, whereas the volume of distribution is talking about all of the body water compartments. So there's a little bit of a discrepancy here. We're no longer talking about just one container. We're talking about multiple containers, the plasma, the interstitial fluid, and the intracellular fluid. So if you see drugs that have a volume of distribution of, say, 15,000 liters, which doesn't seem to make sense, that's because a very, very low plasma concentration can make it look like the drug spread out evenly among a huge volume, but in actuality, it's just a very low concentration in the plasma and a higher concentration in every other compartment of the body. So this is why it's much more accurate to refer to volume of distribution as an apparent volume of distribution, because we're no longer talking about just one compartment or one container. So what factors determine a drug's particular VD? So let's talk about factors that would determine why a drug has the VD that it does. So one is if it's hydrophobic or hydrophilic. So a hydrophobic or lipophilic drug will easily traverse plasma membranes, and the equilibrium would pull them towards adipose tissue away from the plasma. So you can expect that a hydrophobic drug would most likely have a very high VD. Now, on the opposite end, hydrophilic drugs stay in plasma and they do not distribute well throughout the body. So they would have a low volume of distribution. Now, a second factor is if the drug is a weak base. We don't have time to talk about it in the video, but basically weak bases are attracted towards acidic compartments like lysosomes, and then they get trapped there via pH trapping. So a lot of it will distribute out of the plasma, so it'll have a high volume of distribution. Now, a third factor is the size of the drug. Big drugs will tend to get trapped in the plasma, and they'll have a hard time breaking through the plasma membrane. So they'll get stuck in the plasma, won't distribute, and will have a low volume of distribution. 4 would be plasma protein binding. So for example, if a drug is stuck to being bound to albumin, it'll be stuck in the plasma, it won't distribute well throughout the body, and so if it has high plasma protein binding, it will have a low volume of distribution. And lastly, there are patient characteristics that will determine how the volume of distribution interacts, or how the volume of distribution for a certain drug will change based on the patient. So I mentioned this a little bit before, but we usually talk about a 75 kilogram average healthy patient having 45 liters of body water split up between 3 liters of plasma, 12 liters of interstitial fluid, and 30 liters of intracellular fluid. And this is what all of the VDs are reported for. So we could also draw another person, and their weight we don't know. Oh, let's just say it's 100 kilograms. And they're also average and healthy, and they have every other characteristic that matches this patient besides the weight. So they're going to have a higher, a little bit greater than 45 liters of water. And if you were to use a VD for this kind of patient, all you'd have to do is go up to our equation, and you would divide the VD by 75 kilograms and divide the dose by your patient's weight. So in this case, it would be 100 kilograms. And that's all you'd have to do, and then just plug in the numbers as normal, and you'd be able to solve for that specific particular patient. Now, as a general rule, women, people with higher fat content, and older people have less body water per kilogram. So we would need to adjust the dose since there is less body water to distribute into per kilogram. So this way, we would attain the same ideal plasma concentration, whatever that happened to be. So let me back up here. And basically, if this person were had a higher fat concentration, or had a higher fat composition, that means they'd have less body water per kilogram because there's more fat taking the space. So their volume of distribution for the drug, they'd have less water to distribute into, and so we would have to dial down the dose so that the plasma concentration stayed the same. So you can kind of see how that works in the formula, which is pretty cool. Decreasing this number, you'd have to decrease this number, so this number stays the same. Okay, so I think we're ready for a question, so I just have to get rid of all this stuff. So your patient is suffering from a bacterial infection. You prescribe an oral antibiotic that must reach a minimum plasma concentration of 20 milligrams per liter to be effective. The volume of distribution of this drug is 40 liters, and the bioavailability is 25%. What dose would you prescribe? Now, I kind of cheated a little bit. I added the concept of bioavailability here. So let's just work through this together. So if we start with our equation, volume of distribution equals Q over plasma concentration, we can simply start to plug in numbers. 40 liters. It doesn't tell you any patient characteristics, so we're going to assume that it's average 75 kilogram healthy patient. We're solving for Q, and we're given that the plasma concentration has to reach 20 milligrams per liter to work. So what we can do is we could even eyeball it here and say that the Q, the dose, would have to equal 800 to make this equation work. So it would have to be 800 milligrams, and everything else would cancel out. I'll just write things here. But the bioavailability is 25%. So what does that mean? That means that only 25% of the administered dose will be absorbed. And this Q, remember, is referring to the absorbed dose. So that means that we would need to prescribe more than 800 milligrams. And so 800 milligrams is 25% of 3,200 milligrams, or 3.2 grams. So that is actually how much you'd have to prescribe, and then only 25% of this will be absorbed into the body, so then we get an 800 milligram dose being effective in the patient. Distributes among 40 liters of their body to get 20 milligrams per liter as a plasma concentration. But now, what if the patient was obese and elderly? What would you do differently? So basically, being obese and elderly, those are two factors that decrease volume of distribution because there's more fat composition and less body water content in an older person. So you'd have to lower the dose in this patient. So that means you'd have to give less than 3.2 grams. We don't know how much less, but it would be less than for the normal average healthy patient. Alright, so that's all I have. I hope this video was helpful, and I'll see you all next time. Thanks for watching.